Okay, well, since we have seen the concept of work and then we have investigated the new entity of a spring, then let's try to figure out the work done by a spring. So let's imagine you have a system or a spring or a system attached to a spring. So your system is the mass. And you are going to stretch that object to a new position from x0 to x1. I would like to figure out how much work is necessary to bring that system from position 1 to position 2, or from position x0 to position x2. Now remember, if I'm displacing this object from here to here, this is my dr. If I align my dr with my x-coordinate system, then my dr is my dx. So work, which was r1, r2, sum of the forces dr, I can align my dr with my dx. Then I have to consider x0, x1, sum of the forces dx. Okay, now I only want the work due to the force of a spring. So really this is only the one I'm interested in. So the work due to a spring is going to be x0, x1. Then I'm going to use the functional form of my spring force, which vectorially is minus k delta x, or delta x. I'm going for simplicity to use and standard my coordinate system Ix0. So I'm going to be able to use F is equal to minus kx. Now either you use this functional form, therefore you put minus kx dx, and that's fine. You will end up with x0, x1, this is a constant, x dot dx is the same as vector x dot dx vector I. They're both parallel, pointing in the same direction, therefore this is just x dx. Bang, done. Or you can think of it as, instead of using this, you know that f is just kx, and you do a free body diagram on this object. As you do a free body diagram at this position, you know that you have the weight, you know that you have the normal force, and you know that the force is in this direction, and you know that your dx is in this direction. Since f is in the opposite direction as your displacement, you know that the dot product is going to give you a negative sign. Therefore you could have used this as its positive value, and then you cut your free body diagram and realize that your fs is in the opposite direction as your dx. Therefore the dot product, as you take this dot this, will give you the negative sign that you need. So think of it either way. Again, I would suggest to stay away from this, use its magnitude, and then just look at your free body diagram. Since you're expert in doing free body diagram by now, I think usually that's the easier solution. So let's integrate this. Ooh, that looks familiar. We know how to do this. Minus k is a constant. Let's take it out. x0, x1, x dx. We can integrate this easily. Minus k, x2 over 2 between x0 and x1. Therefore the work due to the spring is going to be minus k over 2 x1 minus x0. If I decide to align my coordinate system at x0 as I did here, then x0 is equal to 0. Therefore the work due to a spring to bring an object from equilibrium to a new position, whether you stretch it or compress it, is this. So this is the version that you might see in books or in the literature. This, remember, assumes that you start from equilibrium position, or this is the work done from equilibrium position to any other position that you obtain by either stretching or compressing the spring. Remember that you could start with a position which is already stretched and then compress it. So if you start from here, x1, and you end up here, x2, you definitely need to use that one, and you put 2 and 1 here. So remember, this is only used if you start from equilibrium. If you start from any other direction, that won't work. Okay, so remember, we have aligned our coordinate system dx with dr. If we don't do this, then really we will obtain the exact same results, except we will be dealing with minus k over 2 r2 minus r1. And this is still true, and the nice thing about this is you could have a spring, let's say, being at equilibrium here, then you stretch it to this position, and let's say I'm going to call this position r1. Then let's say this object is stuck on the bar, so it can only move up and down. Let's imagine that this object, due to the force of the spring, obviously is going to have a component here, which would be counteracted by the normal force due to the bar, and it would have this component. So obviously this whole object will be moving up and down, so it might be going to a new position due to this force r2, and this bar might not be entirely vertical, it might be oblique. So let's do it carefully. Maybe this bar is going a little bit like this, so that the stretch at this point is even more than at r1. So now you have a new stretch at r2. Now this, what we call r2 and r1, is the stretch at this particular position, r1 and r2. So r1 will be equilibrium position, and this position, this is r1, and r2 will be the distance between this position and the equilibrium position. So the nice thing about spring is the motion of the object attached to the spring doesn't have to be in the same direction as the spring. All you care is the initial position and the final. So when you write this and you generalize it in r, really this r is delta r2, and this one is delta r1, where delta r2 is the position where your object is minus its position at equilibrium, and that was r1. And r2 similarly is delta r2, which is the position at, the stretching at this particular position minus the position at equilibrium. So springs are very, very nice because you can go in any direction, and all you care is initial and final, or stretching initially and then stretching in the final position, or compression, depending what the system is. So summary: work due to a spring. So remember, the force, the spring force, is kx. The work due to a spring is minus u over 2. And the minus sign is reminding us that if you move a system from equilibrium, let's say you're stretching the displacement, so you're trying to bring this object from position 1 to position 2, the displacement is going towards the left or the right, the force is going towards the left. Therefore you expect, as you calculate the work, which is F dr, to be negative. Therefore the work done by a spring is always, always, always negative, whether you stretch it or you compress it, because in this case dr is in this direction and F is going to be in the other one. Again, F is opposite to dr, the work is going to be negative. So the work for a spring is always, always negative, minus 1/2 x2. Again, this assumes, these two functional forms assume that we start from equilibrium. If you do not start from equilibrium, make sure that you add the initial, final minus initial. Okay, that was the work done by a spring.